is the lamp, I mean the power.
So part of the complexity of the instrument is that because the window is relatively far from the mirror, we have to adjust the table and the heading of the aircraft in order to keep the sun in the spectrograph for the duration of the eclipse. And so the bench moves back and forth so that we can image the sun in test flights at various times of the day, which we'll be doing today. So we'll be, as we take flights over a couple of hours today, the bench will move in order to keep that mirror pointed at the sun through that window. And so the other tricky part, of course, is that since you're on the airplane, there are vibrations, right? The airplane is flying, autopilot. So the autopilot tends to stay on track, but it does all these corrections, so things slosh around. So we have this fiber optic gyro, which generates the error signal of how the plane is sloshing around, and that the tip tilt mirror here corrects that. The mirror also takes into account the rotation of the Earth and the ephemeris pointing. So there are multiple types of motions going into the tip tilt mirror to correct for the long-term motion of the Earth's rotation as the sun moves east to west, and the high-frequency motion of the sloshing of the airplane strip.
And when we're flying, you'll actually see an image of the sun. The slit is all we're actually measuring. The slit is all that goes through into the spectrometer. But we will actually track an image that people are used to seeing. The problem is that this is the first time we've done this, so we don't know how to track. So usually what you do is you'd have an image of the sun, and as the sun moved around, you'd use that motion of the sun to track out the motion of the airplane. But we don't know what it's going to look like during the eclipse. We don't know how to track an eclipse. So what we're actually using is we're using a gyro. That wire. We're using a gyro right here, right there. So that's a gyroscope, and that gyroscope measures what the table is doing and stabilizes the sun. After we've done this flight, we'll be able to then look at that image and tell if the next eclipse we observe, we'll be able to use that image, and if we can, then it'll be better stabilization.
Moving from in this direction, this is north up on the Earth, and it's probably down like that. So we will have complete totality. It will be darker initially on this side, and then as the moon moves off, we might be able to pick up some, still be dark enough to pick up some spectra on the following side after complete totality's happened. So this is kind of giving you an idea of what data we'll be taking. We'll be getting spectra along these lines and the background of this eclipse, and other groups are taking images of the corona, so we'll be able to put our data on top of the image data and understand, the spectra tell you sort of the physical properties of what's going on in the plasma there, and the image data tells you the sort of large-scale structure of where that's happening.